Okay, let's check out question 2 here. If you haven't done it yet, you can pause the video here and check the link in the description below for the PDF of this exercise. All right, so you are riding an ostrich and race down a straight line. So we're back on the ostrich again. And your equation of motion is your x of t equals 0.9 meters per second squared, t squared minus 0.02 meters per second cubed, t cubed. Okay, what is the equation for your velocity as a function of time? So this is something that we had looked at in a previous section here, and we know that the velocity is going to be equal to the time derivative of the position equation, right? So let's figure out what that is going to look like. Well, if this is our position equation here, we're going to take the derivative using the chain rule, right? So the first term is going to be 2 times 0.900 meters per second squared. It's going to be t to the power of 2 minus 1, right? So that's the chain rule for the first term. And now let's do the second term. So it's going to be minus 3 times 0.0200 meters per second cubed, t to the power of 3 minus 1. Okay, so this is going to be our velocity equation. Now let's simplify it a little bit. So what are we going to get here? We're going to get 2 times 0.9, so that's going to be 1.80 meters per second squared times t to the power of 1 minus, looks like 3 is going to be 0.0600 meters per second cubed, t squared. Okay, so that's our final equation here for the velocity as a function of time, just taking the derivative of the position equation. B, what is the equation for your acceleration as a function of time? Okay, so our acceleration, the instantaneous acceleration, is going to be equal to the derivative of the velocity equation, right? And this is the same as the second derivative of the position equation, okay? But we have the velocity equation here, so let's just do the chain rule again to get the derivative of that equation. That'll be our acceleration. So the first term here, it's going to be 1 times 1.80 meters per second squared times t to the power of 1 minus 1, right? And the second term here is going to be, we're going to take this exponent, bring it in front. So that's going to be 2 times 0.0600 meters per second cubed, t to the power of 2 minus 1, right? That's a chain rule. And so we'll simplify it. So the first term here, that simplifies it to just 1.80 meters per second squared, and t to the 0, which is the same as 1, right? Minus, what do we get here? 0. Looks like 120 meters per second cubed, t to the power of 2 minus 1, t to the 1. Okay, so we'll just leave it like this. So now this is going to be the equation for the acceleration, the instantaneous acceleration. Interesting to notice, we're going to start out with some big acceleration, relatively big, and then over time, this second part here gets larger, and so it serves to decrease the acceleration over time, right? Okay, so let's see how that works in part C. So in part C here, we want to know the velocity and acceleration at these 3 different times. So let's try and do that. Okay, we've got velocity and acceleration. Let's do the velocity first. So at t equals 0, we're just going to have to plug in zeros here for both of these, and we see that's going to give us a total of 0 meters per second for our velocity there, right? Now for our acceleration, we plug in a 0 here. So the second term is going to disappear, but the first term will remain. There's no variable there. So it's just going to be 1.80 meters per second squared. So there we have it. There's our results here for t equals 0. Let's take a look at t equals 5 seconds. Okay, at 5 seconds, all right, we're gonna have to plug in a 5 here and a 5 here to figure this out. So let's break out the calculator. So we get 1.8 times 5, so that's 9. So we get 9 meters per second. And what do we have here? 5 times 5 is going to be 25 times 0.06 minus 1.5 meters per second. And we can do this calculation in our heads. This is going to give us 7.50 meters per second. So that's going to be our velocity at t equals 5 seconds. Great. All right, let's look at our acceleration here. So our acceleration, we just have to plug in 5 seconds over here. So that's going to give us a 1.80 meters per second squared minus, what's this going to be? Let's see, 0.12 times 5, that's going to be 0.6, isn't it? Yeah, okay, minus 0.600 meters per second squared. And we can do this math. This is going to give us 1.2 meters per second squared. Oh, sorry, significant figures, 1.20 meters per second squared. Okay, so that's going to be our acceleration here at t equals 5 seconds. So far, so good. Let's do the third part here at 10 seconds. Okay, 10 seconds. What do we have? So again, we're going to plug in a 10 here and here. So for that first term, that's going to give us 18.0 meters per second minus, okay, so there's going to be 0.06 times 100. So it's going to be minus 6 meters per second. And if we do this, we're going to get 12 meters per second. So that's going to be our velocity here. And our acceleration at t equals 10 seconds. Again, we'll just plug in a 10 over here. So that's going to be pretty easy. It's going to be 1.80 meters per second squared minus 1.20 meters per second squared. And we do the math here, and that's going to give us a 0.6 meters per second squared. Is that correct? Yes. Okay. And that's going to be our acceleration here at t equals 10 seconds. Okay, so just plugging in the numbers to our equations. Once we've gotten our equations through differentiation, and we can get our answers here. We can solve for any time. We just plug in whatever value we want. We'll get the instantaneous velocity or the instantaneous acceleration. Finally, part D here. At what time is your acceleration 0? Okay, so to solve this, we basically want to say, well, when our acceleration is 0, what is the time? Well, this is our equation for acceleration, so we can just solve for t when a equals 0. And in this case, we can solve for this. So what are we going to get? We're going to get subtract 1.8 from both sides and divide by negative 0.12. So that's going to be t is equal to 1.80 meters per second squared over 0.120 meters per second cubed. And what do we get here? Well, let's do the math. We've got 1.8 divided by 0.12. That's going to give us 15 seconds. So 15 seconds. At 15 seconds, our acceleration is going to be 0. Right? So we can sort of take a look and see what's happening here. As we said in the beginning, at t equals 0, this is our acceleration because this second term disappears, right? And that's what we found, right? We found our acceleration at t equals 0 is 1.8. But as time goes on, this second term is going to get bigger. And so our net acceleration here is going to get lower and lower. As we can see, it goes down to 1.2 at 5 seconds. And then at 10 seconds, it goes to 0.6. And what we've calculated here is that at 15 seconds, our acceleration is going to be 0. Right? So that's just another way of sort of looking at what's happening here. What happens after it's 0 after 15 seconds? Well, the acceleration will continue to go down, which means now the velocity, instead of increasing, right, our velocity starts at 0, goes to 7.5, then 12. So the velocity is increasing. After our acceleration starts going negative, then our velocity is going to start to decrease. Okay, and that's what's going to happen with a negative acceleration. All right, hope that all makes sense. Let's look at the next question.